and I urge you to take advantage of their help as well. And I hope that you find this course rewarding.
The field of power electronics is concerned with the processing and control of electrical power using high-efficiency electronic circuits. The key functional element in power electronics is called a switching converter. This lecture describes the basic functions performed by switching converters, and it introduces how high-efficiency electronic circuits can be constructed that realize these functions. The switching converter generally includes two input terminals. One is the power input, where a source is connected. The second input is a control input that tells the converter how to process the input power to produce the output. DC to DC conversion is a common function performed by converters in which the voltage of the DC is changed and possibly regulated. So we may change, say, a high input voltage into a low DC output voltage. Rectification is the conversion of AC to DC. And in the process, we may want to control the output voltage, the DC output voltage, and maybe also the AC input current waveform. The inverse of rectification is called inversion, in which we have a DC input and we produce an AC output of a controllable frequency and magnitude. AC to AC cycloconversion involves changing the frequency and the amplitude of the AC voltage. In each of these, the switching converter is the key electronic power processing element, and it is composed of electronic devices as well as reactive elements, and we attempt to build this with very high efficiency. Control is invariably required. We usually want to regulate the output voltage. Although we may want to control currents or other quantities. So we're generally also building some kind of control system that adjusts the control input to the converter, for example, to regulate the output. We can do this with either traditional analog feedback, or nowadays it's economically feasible to use quite sophisticated control using digital microcontrollers. High efficiency is essential in any application that involves very much power. We want high efficiency nowadays, of course, because we want to conserve energy, but in addition to that, it's simply not possible and not economically feasible to process large amounts of power with low efficiency, because our converter will not be able to handle the heat from the power lost. So here's the equation for efficiency. It's the ratio of output power to input power, and the loss is the difference between the input and output power, which we can express in terms of the output power and the efficiency in this way. Now, our switching converters are loss limited. They're limited by the amount of heat sinking that we have and the size of the enclosure. And so for a loss limited converter, with a given efficiency, this limits the amount of output power that the converter can produce. So if we can build a converter with higher efficiency, then we can either reduce the loss and build a smaller converter with smaller heat sinks, or for the same amount of heat sinking, we can get more output power and build a converter that produces more power. So a measure of how good the converter technology is really is the ratio of the output power to the efficiency. And here it's expressed in terms of efficiency. We can solve for this quantity, and it turns out to be efficiency divided by 1 minus efficiency, and it's plotted here. And so you can see that even increasing the efficiency by a few percent can increase the amount of output power, or reduce or increase the ratio of output power to loss substantially. And so our goal is to produce efficiencies that approach 1, which makes the ratio of output power to loss approach infinity. So the higher we can get on this curve, the smaller our converter can be, and the more input and output power it can produce. This drawing here is meant to represent a very small size converter with very large input and output converters. So we have a very small converter with very high efficiency that processes a very large amount of electric power. How do we build a circuit that changes the voltage with high efficiency? Here's a diagram of, in general, the different categories of electrical circuit elements that we have. Resistors, capacitors, magnetics, including transformers and inductors, and semiconductor devices that here are generally grouped into two categories. The first is linear mode transistors, such as Class A amplifiers or op-amp circuits, and the second is switched mode, which is transistors that are operated as on-off devices, such as in a digital circuit, where they're either all the way on or all the way off. In signal processing, such as you probably learned in undergraduate electronics and circuits courses, we usually avoid magnetics. Well, we don't have to, but magnetics generally are more expensive. They're hard to integrate on integrated circuits, and most engineers don't know how to design them. And so for a variety of reasons, we usually ignore or avoid magnetics. But resistors and capacitors are fine. Linear and switched mode semiconductors are also common. In power processing, by contrast, what we want to do is avoid using elements that consume power. So for that reason, we don't want to use resistors. However, capacitors and magnetics are fine, and in fact, it may be easier in a high power application to build a good inductor than it is to build a good capacitor. But we commonly use inductors, capacitors, transformers, and other elements because although they store energy, ideally they don't consume power. We can get that stored energy back at some later time. We avoid linear mode transistors for the same reason that we avoid resistors. That a Class A amplifier, for example, operates with a transistor having voltage across it and current through it at the same time, and so it consumes power. On the other hand, switched mode transistors, or transistors that are operated as on-off switches, are good. They don't consume power. The reason for that is if we can get them to operate close to the behavior of an ideal switch, then what happens is when the switch is closed, there's no voltage across the switch, and when the switch is open, there's no current through the switch. And in either state, the power consumed by the switch, which is the product of voltage and current, is zero. So to the extent that we can make a semiconductor device operate as an ideal switch like this, the semiconductor device will be lossless. So let's do a simple example of how to build a DC-DC converter with high efficiency and using just inductors, capacitors, and switches. Okay, so I'm going to take a simple example with some round numbers here. We have an input voltage I've labeled VG that is a power source, and it's 100 volts. And what we would like to do is change this 100 volts into 50 volts to supply a resistive load. And just for some round numbers, let's suppose the resistance is 5 ohms so that we have 10 amps flowing through our load. Okay, so how can this converter be realized? First of all, let's ask how, in a beginning circuits class, what circuits do you know that could change 100 volts into 50 volts? Okay, well, the resistive voltage divider is one of the first circuits taught, usually in a beginning circuits class, and we learned that the output voltage of the divider is equal to this voltage divider ratio of the load resistance over the sum of the two resistances times the input voltage. So if we adjust this added resistor to be the same value as our load resistor, we'll get a divider ratio of 1/2, and the output voltage will be half of the input. Okay, the problem with this is that the same current flowing to the load also flows through this resistor, and the same power in the load then is equal to the power in this resistor. And so we will have our 10 amps flowing through the resistor that has 50 volts across it. So there'll be 500 watts of loss in this resistor. There's 500 watts going to the load, and we draw 1,000 watts out of VG. So the efficiency is only 50%. At low power levels, it's common to build a series pass regulator circuit that operates almost in the same way as the resistive voltage divider. Except instead of a resistor, we put a transistor that operates in the active region, and it has the same voltage across it that the resistor on the previous slide had, so it dissipates the same 500 watts. With the series pass regulator, what the transistor allows us to do is to build a feedback loop that adjusts the control or the drive of the transistor to regulate the output voltage. But in this example, the series pass regulator is approximately 50% efficient. So we need a very large transistor that can take 500 watts and that has enough heat sinking to dissipate that 500 watts, which is not an easy thing to do. Let's consider instead how to do this function with switches. So instead of an active region transistor, we will use semiconductors that are operated like on-off switches. And here I'm going to draw an ideal switch, but we will realize this switch in practice with transistors and diodes that turn on and off. So let's suppose we have such a switch. We switch it quickly between positions 1 and 2 so that the voltage coming out of the switch network from here to here, Vs of t, has this waveform. So when the switch is in position 1, the voltage Vs is equal to the input voltage Vg of 100 volts. And when the switch is in position 2, the output voltage is 0. And we will operate the switch so half of the time it's in position 1, the other half it's in position 2. Okay, what do we accomplish with this? Well, the switch changes the DC voltage level. So here is this actual waveform coming out of the switch. We can use Fourier analysis to find its DC component, and you may recall from Fourier analysis that the DC component of a waveform is found by integrating the waveform over one period and then dividing by the period. So if you integrate this waveform, the integral is the area under this curve, which is this width dts times the height vg. So we get an area of dts vg. And if you divide by the ts, then what we find for the DC component is that it is d times vg, where d is the duty cycle, or the fraction of time that the switch is in position 1. Okay, so if the switch is in position 1 for half of the time, then the duty cycle is a half, and the output voltage of the switch has a DC component that is half of the input. So the switch succeeds then in changing the DC component of the voltage from 100 volts down to 50 volts. Generally, we don't like to have that switched voltage appear across our load, so we will put a low-pass filter. And here's an LC low-pass filter that can be put in that if we design this filter correctly so the cutoff frequency is much lower than the switching frequency, this filter will pass the DC component, but it will reject the switching frequency and its harmonics and not let them pass through to the load, so that the output voltage is smooth and essentially is just the DC component of 50 volts. So this is a circuit that can change the DC voltage, and it does it with components that are ideally lossless, only switches, inductors, and capacitors, so it can have efficiencies that approach 100%. This is known as the buck converter. Here's one way to realize the switch using transistors and diodes. We have a power MOSFET and a power diode that switch together. And I've also shown here a feedback circuit, say a simple analog feedback circuit, that adjusts the duty cycle. It actually turns the transistor on and off and adjusts its duty cycle to regulate the output voltage. So this is a buck regulator. It's possible to build converters that will change any voltage into any other voltage. Here's an example of a boost converter. that can increase the voltage. So we can build circuits that contain inductors, capacitors, and switches connected in different ways that can actually change any voltage into any other voltage as desired. Here's another example of a single-phase inverter. Here we have two single-pole double-throw switches with the load and filter connected differentially between their outputs, so that the voltage differentially between the two switch outputs looks like this. It can switch between plus VG when the switches are in position 1 or minus VG when the switches are in position 2. And by changing the duty cycle, we can change the average value, and we can actually modulate the duty cycle sinusoidally and make a sine wave of output voltage if we want to produce, say, a DC to AC inverter. Okay, so in this course you're going to learn how to build these converter circuits, how to analyze them and model them to, for example, predict their efficiencies, and also how to design and model their control systems.
SPICE is a program that was originally developed at UC Berkeley in the 1960s, and since then there have been many commercial implementations of it, and one of them, LT SPICE, is freely available now and I think works very well. Here's an example, which we're going to talk about in this lecture. One enters the schematic of a circuit, in this case a buck converter, and then SPICE can numerically calculate things of interest in the converter, such as the waveforms in a transient analysis, as well as other things like frequency analysis plots. So here is a turn-on transient of a buck converter where the output starts at 0. The green waveform here is the output voltage that it computes. It goes through some turn-on transient and eventually settles down to a DC voltage that is approximately, for the buck converter, approximately equal to the input voltage multiplied by the duty cycle. Also here, in red, here is a plot of the inductor current waveform during the same turn-on transient. To get started, what you should do is follow this link to the LT SPICE website, and from there you can download free copies of the software, either for Windows operating system or for the Macintosh operating system. From this Coursera website you can also download a zip file containing the buck converter circuit files for this example. So when you've done that, then you can double click on this file buck.asc, which will open the file in LT SPICE, and that file contains the circuit schematic. Then what you do is press the run button to start the simulation. When the simulation will take maybe 10 or 20 seconds to run. When it's done, then to display a waveform you can click on a node and it will give you the node voltage. Or you can click on an element and it will plot the current through the element. Okay, here I have opened LT SPICE and opened the buck converter schematic. What we have here, this is the buck converter power stage with the input voltage VG of 24 volts and output voltage that supplies a 5 ohm load resistor. Here is the LC filter, and the switch in the buck converter is realized with this power MOSFET and power diode. The circuit has a driver and a pulse width modulator. These are called behavioral models or mathematical models of these functions that we have developed for this Coursera course. So the pulse width modulator takes a DC input voltage, here V duty, that has a value of 0.4 volts DC, and it produces an output logic signal C that switches on and off with a duty cycle that is determined by V duty. Here the duty cycle of C will be 0.4. It has a switching frequency that is set by the pulse width modulator, and you can right click on the pulse width modulator and enter the switching frequency. In this case the switching frequency is set to 100 kilohertz. This signal C goes into the driver. The driver produces an output voltage to drive the gate of the MOSFET with respect to its source, at the proper voltage to turn the MOSFET on and off according to the signal C. So to run the simulation, we put the cursor on the run button, the little running person there, and click it. It will take maybe 10 or 20 seconds for the simulation to run. Okay, the simulation is done. LT Spice has opened a new window here for plotting waveforms, and we can move the cursor over the schematic to different places to plot different waveforms. So first let's look at what the pulse width modulator is doing. I will move the cursor over the pulse width modulator input. The cursor changes into a little voltage probe signal, and if you click there, it will plot that voltage. Okay, so the voltage is 400 millivolts or 0.4 volts. We can look at the output voltage that the pulse width modulator makes. So I'll move the cursor over C. Okay, this is the blue signal here is switching up and down with a frequency of 100 kilohertz. Let's get the magnifying glass and zoom in on part of this, maybe over here. So the blue waveform is C, the control signal. It has a switching period of 100, or switching frequency of 100 kilohertz, corresponding to a switching period of 1 over 100 kilohertz or 10 microseconds. And the signal is high for the duty cycle times 10 microseconds, which would be 0.4 times 10 is 4 microseconds. Okay, I'm going to erase these waveforms, and now we'll look at some converter waveforms. So to erase a waveform, what you do is right-click on the name of the waveform here on the plot. So right-click on the PC, or you tap the trackpad with 2 fingers on the Mac and select delete this trace. Let's plot now the switch node voltage. So we have to click on the window of the schematic, and then when we hover over the switch node right here at the point between the transistor and diode, we can click with the oscilloscope voltage probe symbol and get a plot of the switch node voltage in green. So when the MOSFET is on for the DTS period, the switch node is equal to VG, like this. And we have 24 volts for VG. And then when the transistor is off, the diode comes on, and the switch node voltage is equal to ground, essentially, and so we have 0 volts or a low voltage. Let's plot the inductor current also. So when I hover the mouse over the inductor, the pointer turns into a little current probe to measure current in the inductor with positive current in the direction showed by the red arrow. So let's just click there. And the blue trace then is a plot of the inductor current. It goes up and down like this. It's switching or varying between about 2.6 amps and about 1.1 amp. Okay, finally we can plot the output voltage. So we'll take the mouse and hover over the output voltage and click. So the red line is the output voltage. It looks like it's between 9 and 10 volts. Now we expect the output voltage of the buck converter to be the duty cycle times the input voltage. So V should be equal to the duty cycle times VG. VG is 24 volts and the duty cycle is 0.4. So 24 times 0.4 is 10 volts. And what we find is the output voltage is a little bit less than 10 volts, but it's close. The SPICE simulation includes some of the loss mechanisms in the converter. It includes the forward voltage drops of the transistor and diode. Here I put a little resistor in series with the inductor to model the resistance of the wire used to wind the inductor. And these things all cause voltage drops that make the output voltage a little less than we would ideally expect. We'll model those things in Module 3 of this short course and develop some equivalent circuit models that predict more accurately what the output voltage is. Let's plot the input current waveform. I will select the schematic window and hover the mouse over VG. You can see that again it turns into a current probe symbol, and the arrow is pointing from top to bottom in VG, which means current is flowing from plus to minus through VG, which is backwards from the direction we actually expect the current to flow. So SPICE is going to plot this current with a negative sign, or make it negative. Here's a plot of it. When the transistor is on, the current follows the inductor current, again with a minus sign. When the transistor is off, the transistor current is 0, and so the VG current is 0 also. We also have this current spike here, and this is caused from the reverse recovery of the diode and from the transistor and diode switching times. This is another source of loss called switching loss, which we're going to study in the next short course of this course. We can measure voltages and currents using SPICE. What we do is we press the control button and click on the name of the waveform, and then a window comes up that tells us the average value and the RMS value of the waveform. So the current drawn out of VG, this I of VG, has an average value or DC component of here 707 milliamps. So we're drawing 770 milliamps on average of current out of VG. This current includes the current spike during the switching times. We can use this function to measure input currents and output currents and voltages as well, and calculate average powers and efficiencies of the converter. Likewise, we can plot the current that the gate driver draws out of its power supply. So what I do again is select the schematic window, hover over the power supply for the gate driver, and click there, and we'll get the current waveform of the gate driver, which looks like this. The gate driver must draw current out of its power supply to turn the MOSFET on, and so we see these current spikes happening. So the gate driver requires some power to operate, and we can measure the voltage and current of the gate driver and calculate its power as well. So I will control click on that waveform, and here we see that there's an average current of 14.876 milliamps drawn out of the driver. That's the average value of the waveform. It's actually coming in spikes that are considerably higher. But the average current is the DC component of current, and the average power drawn out of the gate driver supply then would be this average current multiplied by the gate driver voltage of 12 volts. Briefly, here are a few more details regarding the models that we have provided for the pulse width modulator block and the gate driver block. The functionality of this block is that it produces an output logic signal C having a duty cycle given by this formula. So it's a function of VC, the input voltage. It can have an offset, and it can also has a gain, so it's divided by some effective number V sub m. You can right click on this block to set values for those things, the offset voltage and Vm. Right now Vm is set to 1 volt, the offset is set to 0, so the output duty cycle is just equal numerically to the DC value Vc. The block also limits the duty cycle. It has to be between minimum and maximum values, which can be set as well. And you can set the switching frequency again by right-clicking on the block and typing the number in the window. The gate driver block, similarly, is a behavioral model that represents key features of gate drivers. So what you do is you apply the logic signal C to this input terminal of the driver. The driver actually measures its input voltage with respect to this input reference, which here is tied to ground. And then it produces an output voltage here with respect to the driver VDD or VSS signal here. And what we do is we apply these two terminals to the gate and source of the MOSFET to turn the MOSFET on and off. The output ground or reference of the driver need not be the same as the input reference. We also have to supply power to the driver to make the circuit work, and so here we've connected a 12-volt power supply between the input power supply VDD and its ground pin VSS. One last point, let's look again at the complete simulation for the output voltage and inductor current. So I will again plot the output voltage, and we'll plot the inductor current. And this is a plot from t equals 0 all the way to 5 milliseconds, and you can see what happens during this turn-on transient. All the signals are starting at 0 with the converter turned off, and then when we turn on, the circuit goes through some transient where the output voltage rises and there's some kind of here overshoot and ringing in both the current and the voltage, and eventually the circuit settles down into steady state. So here's a steady state output voltage and a steady state inductor current. We can measure those values as well using SPICE. So we zoom in at some point after the transient is done, and then we can control click to measure the average voltage, 9.2855 it says. So again, a little bit less than 10 volts. We can also control click on the current to measure the average inductor current. It says that is 1.8573 amps. Okay, the homework assignment for this week is to download a boost converter